Okay, so now what we're doing is, like we said before, we're taking the resultant force and we're breaking it into two component forces. And what we're doing is setting up these component forces so that they're 90 degrees or perpendicular from each other. So Kyla pulls a rope attached to her sleigh with a force of 200 newtons. If the rope makes an angle of 20 degrees with the horizontal, determine the following. What I'm going to do before I even get to any of that is I'm going to create a picture of what's going on. So here is the sleigh. We're going to do one of those old school sleighs that hook up like this. Those are the ones that are fastest by far, in case you're wondering. And then she's pulling the sleigh with a rope. Okay? So our vector heading upwards is essentially our rope. And we said that it makes an angle of 20 degrees with the horizontal, or in other words, the ground. Okay? So this arrow here represents our ground, and this arrow here represents our rope. It says that the rope is being pulled with a force of 200 newtons. Okay? They want us to figure out what the force that pulls the sleigh forward and the force that lifts the sleigh. So when I say we're breaking this into two different components, I'm going to get a different colored line here. And what we're going to do is this resultant force, the one in the middle, is going to be broken into a force like this, that is horizontal, and another force that is perpendicular to that, or vertical. Okay? So in other words, we're creating what we know as a right angle. Think of this as the force along the x-axis and the force along the y-axis. Okay? These two forces together will give us our resultant force. Okay? So what I'm saying is if I had a force pulling directly upwards and a force pulling directly to our right in this case, we would end up with this force in the middle. But the difference is they've given us the force in the middle, so we have to determine those two other forces. So we're working backwards. Well, what we're going to do is, because this is perpendicular and we're used to moving our vectors around, that's exactly what we're going to do. I'm going to move this vector over here, and we're going to create a right angle triangle from that. I'm going to move the arrow too. Okay. So we now have a right angle triangle that we can work with. Now that force that we moved over is still the force along the y-axis. But the reason we turned it into a triangle is so we could use our primary trig ratios to solve this. Okay, so we're going to use SOHCAHTOA, if that's what you guys are used to calling it, to solve this triangle. So, let's zoom in. With that information, we get to it. I'm going to try to find the resultant, or the magnitude, okay, of force X, the force that would pull it forward. That's what question A is giving us. So the magnitude of the force, or the force along the x-axis that's pulling this forward, would be equal to, well, according to our SOHCAHTOA, this is the angle I'm working with. This is the adjacent angle, and the, sorry, not angle, side, and the hypotenuse is the side that we actually have a measurement for. Anyone know which of the three we'd use then if we have adjacent and hypotenuse? Cos, that's right. So we're looking for cos 20. Okay. Well, let's figure out what cos 20 is. What that means is cos 20, we know, is also equal to adjacent, which is our f at x, divided by our hypotenuse, which is our 200 newtons. Okay. So in other words, this one here divided by 200 newtons. So make sure that is an equal statement. What we're going to do is we're going to move the 200 to the other side of the equation. So our resultant force X, yes, someone please equate this for me. Cos 20 times our 200 newtons, or 200 in this case. What would our resultant force be? 187.9? Great. 187.9. So the force that is pulling the sleigh forward, or that component force, is 187 newtons. And it's pulling it directly to the right, or to the east, or forward, whichever way you like to describe that force. Okay? The other force we're working with is question B, is the force that lifts it upwards. So the force along the y-axis. Okay? So same idea, only difference in this case though is our angle. What side is this compared to our angle? Opposite. So what primary trig ratio will we use in this case? We use, if we have the opposite and the hypotenuse, anyone remember? Sine. We'll use our sine ratio for that. Okay? So, question B. The resultant force is our opposite of the hypotenuse. So the resultant force divided by the hypotenuse, which is again 200 newtons, that's an N, is equal to sine 20 in this case. Exact same procedure as before. The resultant force along the y-axis, or the force that is lifting it upwards, is sine 20 times that force, which is 200 again. Our force is 68.4, I think, right? So, let's try to make sense of that. What this is saying is, and if I'm just going to recreate another horizontal line going upwards, just so we can see the two component forces at work. Okay. The one across the bottom was 187.9 newtons, and the one going upwards was 68.4 newtons. Okay? In other words, this one's 68.4 newtons, which makes sense because it looks like a much stronger force is pulling it forward than the force that is pulling it upwards, which means that it would be lower than 45. If we have two equal forces, the angle this would make with the ground would be 45 degrees. But because the force pulling forward is stronger, it causes the angle to be more acute than 45 degrees. Does that make sense?